Today we're going to take our vectors a step farther. We're going to move into the calculus of them, and we're going to talk about what are called vector-valued functions. Now, after doing a little research earlier today, I found that vector-valued functions are a huge component of multivariable calculus. So it's actually laying the foundation of something for a calculus course beyond this. So we talked about vectors yesterday. It's just one vector here ends there. But now we're going to put vectors into what are called vector-valued functions. So instead of just like 4i plus 2j, we're going to have what's called a vector-valued function in the form f of ti plus g of tj. So now our vectors are going to have t's in them. This t is a parameter, just like parametric equations, but it is not necessarily time. Okay? So t can be negative, and that's okay. So what we're doing is we're kind of doing a pairing of parametrics and vectors into the same problem. All right? So a vector-valued function takes a variable t and spits out a vector. Usually when you think of a regular function, you take in an x and you spit out a y. Okay? Parametrics, you take in a t and you spit out an x and a y. But here, we take in a t and we spit out a vector. That's what our result is. The domain of a vector-valued function is the set of all t for which both component functions are defined. So what we do is we look at each component individually and find the crossover of the domains. Okay, so we're going to do a little review with domain. This used to be tested on the AP exam. It's not anymore, but it's a good thing to play with and practice. Okay, look at what's in front of the I. What numbers am I allowed to plug in for t? Anything
except above.
0 and above will work, but also you can go down a little bit farther. You can go all the way down to -1. Can you include -1?
No. Yes.
The square root of 0, is that a number? Yeah, the square root of 0 is 0. So for this part, t can be greater than or equal to -1. That's its domain. That's what it can be.
Can it be -2?
That would be, and that'd be I, and then we get into the imaginary. So we're talking about what will make it real.
So do you have to mention that in the domain?
No, everything that we do in this class is considered real numbers. Complex doesn't come until much later, college math. Okay? Now, ln's. What kind of numbers can you not take the natural log of? 0 and negative numbers. You can't have the ln of 0, you can't have ln of negatives. So, I'm going to actually do this in terms of a mathematical problem. What's inside here has to be greater than 0. Does that make sense? And this way I can find the domain very quickly. What's inside the ln has to be bigger than 0. So if I move the 4 over, I get -t is greater than -4. If I divide by -1, what do I need to remember? Flip the sign. So t is less than 4. Anything less than 4 will work. 4 will not work because that will return a 0, and I can't have the ln of 0. So the true domain of the whole thing is the two of these where they overlap. So if it has to be greater than 1, but less than 4, it's where they meet in the middle. So my true domain is -1 is less than or equal to t is less than 4. So anything between -1 and 4 will give me an answer. Yes, sir?
We can't take the ln of 0, right?
Correct.
So should it be 0 is less than t, which is less than 4? Or is that, how does that work?
Good. Oh, good job. Okay. If I plug a -1, now wait a minute though. If you plug -1 in here, what are you going to get? You're going to get 5, which is okay. So that's already taken care of right here. This says that t has to be less than 4. So I can't plug in +5 or 6 or 7 or 8. So this is telling me I can only plug in numbers between -1 and 4. Okay? Bigger than 4 is bad for this one. Less than -1 is bad for this one. So anything in the middle is fine.
What about 0?
0 in here is going to be an ln of 4. You see it?
Oh, never mind. I was thinking.
Yeah, you were thinking that it was going to be ln of 0. Okay. All right. Let's look at the next one. We have e to the -ti sine inverse t of j. What about e to the negative t? Can I put anything in that exponent I want to? Can I put positive numbers up there? Yeah. Can I put negative numbers up there? Yeah. Can I put 0 up there? Yeah. So here is all real numbers. Anything works. Anything goes for e. Anything goes. Okay. Sine inverse is a little bit different. We haven't thought about sine inverse's domain in a while, but listen to what I'm saying. The domain of sine inverse is the range of sine.
Negative 1 to 1.
So it has to be between -1 and 1. Does that make sense? Sine and sine inverses switch their domain and ranges. So the domain of sine inverse is the range of sine, and the range of sine is -1 to 1. So these two have in common, where do they overlap? Right here. So my answer is -1 is less than or equal to t is less than or equal to 1. Are we good with that? All right. Any questions? So far, so good. Okay. Now, number 2 says to sketch the vector valued function r of t equals t minus 5i plus j. So if you plug in t equals 0, you're going to get -5i plus 1j. So that means you go -5i up to 1j. 1 is a huge jump here. Draw the vector. Then you plug in 1. That would be -4i plus 1j. So you move over to -4, go up to here, draw the next vector. And you just keep going and going and going. So what are you seeing? It's just a ton of vectors. Okay? So this could represent a fan that oscillates. And it's talking about its magnitude. It's different on every one of these. Are all these vectors the same length? No, the ones on the outside are longer than the ones on the inside. Okay? So this can be a representation of something like that. But when we come down here, it says in vector valued functions, we're usually interested in the path of the endpoints of the vectors. So all we really usually care about are the tips of the arrows. What kind of path do they make? And in this case, if we take the tips of the arrows and connect them, we just have a straight line at 1. Okay? So, because of the fact that we're focusing just on the endpoints of the vectors, when we graph this thing, we can graph it parametrically very, very easy. There is no vector graphing setting on your calculator. So what we do is we change our graph to parametric form. We change our equation to parametric form. We're going to change it to parametric form to graph it. So, what's in front of the I? Remember, I is a vector going in the left and right direction, usually in the right direction. That's your x. And what's in front of the j, since j goes up and down, that's your y. So x here is 4 cosine t, and y is -2 sine of t. So all we do is pull out those functions in front of the I and j to create our parametric equations. Okay? So now take your calculator, please. We've got to do some major adjusting. Yes?
Isn't of the general form for the I minus j, so it's minus j, that's the general form, correct?
The linear combination form, yes.
So wouldn't it be positive 2 sine t?
No, actually the general form is this plus this.
Oh, okay.
So we do bring the minus sign down. It is I plus j. I'm sorry. Okay? So I have cleared my RAM just because everything was reset. So the first thing I need you to do is push the mode key. Everybody needs to do this because your calculator is very much not in the right format for this. First thing you need to do is put it back in radians, because notice it tells me t goes from 0 to 2 pi. Okay? So first thing you do, put it back into radians. The second thing you need to do is put it in parametric mode. It's probably in polar mode. So let me move this up so you can see what I'm doing. So it needs to be in radians, and it needs to be in parametric right there. So those two things need to be set. Are we good? Okay, so let's go to y equals and type in our two functions. We have 4 cosine t, push enter, -2 sine t. Do not graph it yet. We have to set the window. So go to the window, please. Now, the paper says, my calculator's over it, t is supposed to be between 0 and 2 pi. So it needs to be 0 to 6.28. Is that what your calculator says? Okay, we didn't change it to anything else. Okay, so we're good there. Your t step is just 0.13, blah, 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 or you can just put 0.1 is fine. 0.1 will do the same thing. Okay? Now, every time from now through tomorrow that you see a grid, please set your window to this grid, but go one number beyond what each of the x and y axis say. So this one shows -4 to 4, so I'm going to go -5 to 5. That way you can see everything with a scale of 1. Okay, now do not push graph just yet. This will give you a nice picture based on what we can see. I want you to notice as it graphs, where did it start and which direction did it go, because that does matter. Okay, so now push graph as soon as you got all that set.
Starts on the
It starts on the right, doesn't it? And which way did it go?
Curve down.
It curved down. Is that clockwise or counterclockwise?
clockwise.
That is clockwise. It went clockwise, which is kind of backwards. Now, looking at the equations, can you tell me why it went clockwise?
Negative sign?
Because the sign is negative. Because as it went cosine positive, sine negative. So the first place it ended up going was quadrant 4. Okay? So let's draw this ellipse. How far out does it go on the left and right? To 4. So we're going to put a dot at 4 and -4. How high up and down does it go?
2.
It goes up to and then down to 2. So to make your ellipse round, if you draw ellipses and they look like diamonds, I did for a long time. Let me show you my little trick I came up with. And watch me just botch it really bad. If you start at the top and make a letter C going through your points, it tends to make things nice and round. And I missed my point. Okay? And then on the other side, do exactly the same thing backwards. And it turns out a little bit rounder than it would if you tried to connect all 4 of them with one pencil drawing. Those of you who are artistic, you can already do it right. That's not me. That's not me at all. Because like I said, all we care about are the endpoints of the vector. So basically it's drawing vectors starting right here and going around the circle and filling it up. Okay, so please label the starting point as t equals 0. So where did it start? Right there, t equals 0. And put arrows on the curve to show which direction it went. Went like this, like this, like this, and like that. So that's how we draw a vector valued function, okay? I cannot imagine them on the AP exam giving you a question like this without a calculator. I just can't. Okay? Any questions on that? So, the reason we do parametric, polar, and vector all at the same time is because they all kind of mix together. We changed parametrics to polars. We changed polars to vectors. We changed polar to rectangular. Rectangular is the old-fashioned way we've been graphing. Now we're going to talk about changing rectangular to parametric and then to vector value. So you can represent any rectangular equation by a vector valued function. So you can turn any one of these regular y equals x equations into a vector valued function. And we're going to talk about how to do that. It's not very hard. They didn't leave us a whole lot of space. It doesn't take a lot of work. Okay? Now, the first thing we're going to do is write it in parametric form, and then we're going to change it to vector form. It's kind of the backwards thing of what we did for the one above. Okay? When we did this, we did it really quickly on the day we did parametrics. So the first thing you do is you say x equals t. There's more than one way to write a parametric equation. This is the easiest way. X equals t. Now write the y equation with all t's. So it'd be t to the third minus 2t squared plus 3t minus 1. Done. That's parametric form. Okay? Yes, sir?
Did we do that in any of our previous notes?
We did it 2 class periods ago.
Oh.
Okay? So now we're going to put it in the R of t form, the i's and j's form, the vector valued form. So the R of t is going to be, now hang on just a minute before I write it down, come back up here. When it was in R of t form, we pulled out what was in front of the I to be x, and what was in front of the j to be y. Now we're going backwards. So what am I going to write in front of I? Just t. Ti. Plus, I write what's in front of y, t cubed minus 2t squared plus 3t minus 1 with a j. And there's my answer. That is the vector valued form of that rectangular equation. So, up until algebra 2, we only know about x's and y's equations, right? And now we have those, rectangular, parametric, polar, and vector valued. We now have 4 different types of equations that you can write. Any questions on what I just did?
No.
That's pretty easy stuff, huh? Yeah, we like that. All right, turn the page, please. Now, this is what we're going to do that's a little bit different. All right, look at the top of the page. What we have here is a bunch of math writing, okay? Over the year, we have been practicing how to read math, especially at the college level. Your professors in college are going to expect you to be able to read and understand what it says, okay? So what I'm going to do is I'm going to give you a few minutes to look this over. I want you to read it over and see if you understand it. If you understand the equation, I want you to put a check mark by it. I get it. And the ones you don't understand, we'll come back and stop and see if we can decipher them together. So take a few minutes to read this and see what you understand and what you don't. All right, let's take a look at number 6. Let's talk about how to do limits. So we're going back to limits. Do you like limits?
No.
Yeah, yes you do. You like limits. Okay, we take the limit of each component, the I term and the j term. Can you tell me, if I'm doing just the limit as t approaches 3 of ti, can I plug a 3 in for t? Yes, get an answer. Can I plug a 3 in for t on the second term? No. So, if I do, I'm going to get 0 over 0, which means keep going. So what can I do? I can factor, or I can do L'Hopital. Do you have a preference? L'Hopital. We all like L'Hopital. Okay. So what I have to do is write L hop out to the side, which means I'm going to do L'Hopital. And so we're going to do limit as t approaches 3. Now I know I can do the first term, but I'm not going to do it until I do all of them at the same time. So this will be ti plus, what would the fraction be after doing L'Hopitals?
2t.
2t over 1j. And now I can plug in the 3. So my answer will be 3i plus what? 6j. That's my limit. Now the limit of a vector valued function is a vector. Okay? Now, do you remember what this is in component form? What would I write? 3 comma 6, right? And what does that mean? That means there's a vector over 3 and up 6 is where it's what is? The head is. And the tail is at what?
At 0.
At 0, 0. Okay. So that's what this means. Let's do the next one. Okay. Can I do the I component without any problem?
Yes.
Yeah, I can plug in 0. Can I plug 0 into the j component? No. I'm going to get 0 on the bottom and 0 on the top, which means I need to go again. So I guess we're going to do L'Hopital's again. So this will be limit as t approaches 0. What is the... Now, I'm not taking L'Hopital's of the first one. I have to just recopy it. Okay? Minus, I'm doing L'Hopital's on the second term only. Cosine of t over 2j. You can't do L'Hopital's on something that doesn't need it. It'll give you the wrong answer. So now I'm good to plug in the 0. What do I get when I plug 0 into the first term? 1i minus what? 1/2 j. Do you agree with that? Okay, that one's done. All right. I need to do the last one because it has an infinity on it. can I plug infinity into the first term?
Oh, yes.
Will I get an answer?
No.
Yes, I will. Yes, I will. Because this first term is the same thing as 1 over e to the t. Do you agree with that? And the only time you can use L'Hopital's is if you get infinity over infinity. The bottom will be infinity, but the top is 1. Okay? So this one's ready to go. This one, however, is going to be infinity over infinity. Do you agree with that? So we are going to do L'Hopital's again. So we're going to write this as limit t approaches infinity. We're going to write the 1 over e to the t plus, what is L'Hopital's going to give me on the next one? 5 over 1 j. So when I plug infinity into the denominator, what is that whole fraction going to become? It's going to be 0. I forgot my I. Squeeze the I in there. So this is going to equal 0i plus, there's no place to plug a t in infinity in here, so it's just 5j. This answer and just the 5j part are both considered correct. So you don't have to write the 0i. You could just write 5j. It's up to you. It's not wrong if you leave it on or take it off. Okay? Questions? Okay, let's talk a little bit about continuity. Determine the intervals on which the vector valued function is continuous, because this will be on the homework. We're only going to do letter C. So we want to know basically what the domain is, where it's going to be continuous. The limit is equal to the y value. So what am I going to be looking at for cosine? What can I plug in for t? Anything I want. So that's still all real numbers. What about cosine inverse? That is back to the -1 to 1. We talked about that earlier. The domain of cosine inverse is the range of cosine, which is -1 to 1. So this thing is going to be continuous between -1 and 1. Okay. So I believe the homework doesn't ask specifically for domain questions. It does ask for continuity questions, which is done basically the same way. Are we good? All right, let's move on to the next page. And I believe this is it. Yep. Okay. Oh, look, another box of stuff to read. Okay. My first period groaned. Okay, we'll just kind of go through this one quickly. Does the first box make sense to you? I mean, the first line. We're talking about derivative. If you're taking the derivative of two functions that are added, complete the sentence. What does it say? You take the derivative of each one individually. Okay? So if you multiply a derivative, if you take the derivative of a function multiplied by a scalar, you just take the derivative of the function and then multiply it by the scalar. Okay? It's the same. Remember how we can pull numbers out of intervals? You can pull numbers out of derivatives. That's the official, it's sitting there and not being used. Okay. Now, there is a mistake on the third line. They invoked the wrong rule. What rule are they doing on that third line right there? That is product rule, not power rule. So this is product rule. Okay, it is product rule. Doesn't it? Do you see the 1D2 and 2D1?
Yeah.
Okay, now the vector product rule, what's the difference between these two? This one is multiplying by a function, but you still do a product rule situation. Here, it's two vectors multiplied together, and you definitely do product rule for that. Okay? Now, when you get down to the integrals, it gets a little ugly. Let me tell you this. From my experience of doing these, I don't really care for the first line. I care for the second line more. I like the C inside the integral with the problem. So basically, when you integrate a vector valued function, you integrate each component separately. And then each component gets its own C. F of t gets its own C, and g of t gets its own c. And there are two different c values that you have to solve for. We're going to do a sample problem of this in a minute. If it is a definite integral, this is just telling me that I take the separate integral for each term and plug in the a and the b. Okay? Are we good on this? All right, let's do a couple of these. We have f of t right here, u of t here, v of t here. I like to do that just because it gets all jumbled together. So many letters. Find each of the following. We're going to do it in one way, not two different ways. It takes too long. We're going to take the derivative of a function times a vector. So, you could do just the function times the vector first and then take the derivative, or you can do it a different way. So I'm going to do it multiplying the two insides together first. So I'm going to recopy the d dt and the bracket. F of t is t squared plus t times u of t, which is 1 over ti minus j. Okay, the first part does not have i's and j's, the second part does. So I can go ahead and just distribute. I'm going to pretend like I'm not taking the derivative. This is what we did on the previous page, just distribute it. So I'm going to recopy the d dt, t squared plus t times 1 over t. T plus 1. T plus 1i. So basically when you multiply by 1 over t, it makes the power of t drop by 1 every time. So t squared becomes a t and t becomes a 1. And then the j, there's a 1 in front of it. So it's this times 1, so it's going to be minus t squared plus t j, like so. Okay. Now I'm only taking the derivative of one thing. So I do each term individually. What is the derivative of t plus 1? 1. So it's 1i. Remember, i's and j's are basically constants here. They're like pi's. They're just kind of sitting there. Minus, what about the second term?
2t
Plus 1j. And that's your answer. I took the derivative. Yes, sir.
How did you get like t plus 1 from t squared plus t?
I multiplied the t squared plus t times this 1 over t right here. I distributed it in. So if you put t squared plus t on top of t and separate the fractions, that's what you get. Okay? Any other questions? Excuse me. All right. The derivative of u of t times v of t. I remember you guys doing an AP practice assignment way back when, where you could have multiplied those two first and then taken the derivative, or taken the derivative right now, which would include product rule. So, do you have a preference as to how we do this? Would you rather not do product rule?
No problem.
Let's kind of avoid product rule. So we're going to do basically what we just did. d dt of u of t, which is 1 over ti minus j, times v of t, which is t squared I minus ln of t j. Close my bracket. I did it the other way last period, and it was ugly. It was very ugly. Okay, remember that multiplication is like dot product. You multiply the ones in front of i's, you multiply the ones in front of j's, and you add them together. So d dt, parentheses, 1 over t times t squared. I'm going to go ahead and write it all out. 1 over t times t squared plus, there's, what's in front of this j? Negative 1 times negative ln of t. That's how you multiply the vectors. Multiply the x's, multiply the y's. Yes, ma'am?
Where did the plus sign come from?
That's the formula that was on the previous page. It was before you got here. Okay, so d dt, what does the first term clean up to be? Just t, right?
Yeah.
Plus, what does this become?
ln.
Ln of t. So now I'm just taking the derivative of that I don't even have i's and j's to mess with. That's nice. So what is the derivative of this? 1 plus 1 over t. Done. All right, we have two more to do. We're going to do not A, we're going to do B and C. We're going to talk about how to do a definite integral and how to do an indefinite integral, because either one of these could show up on the quiz on Friday. All right, definite integral, according to the rule, which is off the page, you do the integral of each one individually, or the antiderivative, so to speak. And then you put your bracket on the back, just like we've done in the past. What is the antiderivative of e to the negative t? Negative e to the negative t. Now this is the ones that don't get a plus c because it's definite. Put the I on it. The I just sits there, remember. Plus, what about the next term? 1 over t plus 3. What's the antiderivative of that? That is an ln of the absolute value of t plus 3. Top is derivative of bottom, so it's ln. Put the j on it. Put your back bracket, 0 to 1. So you just took the antiderivative of each term. The i's and j's kind of just sit there. And now we plug the values in. So we now plug in negative e negative 1 I plus ln of what number? Of 4. Now since 4 is positive, I don't need the absolute values anymore. ln of 4j minus, because remember it's top minus bottom, negative e to the 0 I plus ln of 3j. Okay, so what we do now is combine like terms. So we have negative e to the negative 1 and then negative e to the 0. What is negative e to the 0 again? 1. So minus negative 1 is going to be plus 1. Agreed? So we have negative 1 over e plus 1 with i's. And then we have ln of 4 minus ln of 3. How do you combine it into a single log? ln of 4 over 3j. And there's your answer.
Drop that again.
As soon as you plug in a value for it, you take the absolute value of that number. So when I put in a 1, I got a 4. The absolute value of 4 is 4, so I can take them off.
It's just to make sure that it's not negative.
Correct. It's to make sure the value in the absolute in the ln is not negative. Okay? Anything else? Okay. Last problem, and that is finding the indefinite integral of this. If r of 0 is this is my initial condition. And this is going to help me find the c values. Okay? So we're going to start this one just like we did the other one, but every time we take an antiderivative, we've got to put a plus c on it. So r of t is going to be, parentheses, what is the antiderivative of sine of 2t? Almost.
Oh, I mean negative 1.
Negative. It's going to be negative cosine of 2t, but it needs a 1/2 in the front to balance out the 2 that would come out of it. Put a plus c1 afterwards, and then an I. Okay? So the I term gets its own c value. And now we do the same thing for the j term. Look at what's in front of j. It's not ln. Does anybody recognize it?
It's a tangent inverse.
It's inverse tangent, yes. So this is tangent inverse of t plus the second c2 with a j. So we took the antiderivative of each term individually and gave each one a t. Yes?
Why are the C's different?
Why are the c's different? Because they could be different numbers. And once we go through the math to show you, I think it'll make sense. Yes?
So when you take the antiderivative of the sine,
Yes?
I'm confused.
Okay. You know it's going to be negative cosine for starters, right?
Oh, okay, yeah.
So when you take the derivative of cosine back to get sine, it's gonna throw a 2 out at you that you don't want. So you have to put the negative 1/2 in there to counteract
You
it.
always do the reciprocal.
The reciprocal, yes ma'am. Okay? Now, do me a favor, and I think this will help make it more understandable. Tell me what this is in component form. What is it going to be? Not 1/2 0, 1/2 1. Okay? So this math sentence over here says that when t equals 0, because this is r of t, when t equals 0, x is 1/2 and y is 1. Does that make sense to you? When t is 0, x is 1/2 and y is 1. That allows us to take and individually solve this parentheses and this parentheses. So if we plug in t equals 0, we're going to have negative 1/2 cosine of 0 plus c1 equals the x coordinate 1/2. What's in front of the I for the equation has to be what's in front of the I up there, the 1/2. And then the other side, tangent inverse of 0 plus c2 is supposed to equal the y coordinate 1. So that gives us our two equations to solve. What's plugged into the r is what t is, and then we set each one equal to what it tells me the components are supposed to be. Okay? And now we just solve. What is cosine of 0 again? 1. So negative 1/2 plus c1 equals 1/2. So what does c1 equal? Positive 1. Agreed? Okay. Now let's do the other one. What is tangent inverse of 0? Where is tangent 0? At 0. So 0 plus c2 equals 1. So c2 in this instance happens to also be 1. Will they always be the same number? Definitely not. Okay, so now we go back and take our equation that we got for our antiderivative and write it with those numbers in there, and you're done. So r of t equals negative 1/2 cosine 2t plus 1i plus tangent inverse of t plus 1j. And there's my integral. We're good? All right. That's it for today.